Have you ever gazed at the night sky and wondered if there's a hidden code behind it all? Well, you're not alone. The universe, with its endless galaxies, stars, and cosmic wonders, operates according to a secret language. This language, this cosmic code, governs everything from the smallest particles to the largest cosmic structures. Now, let's dive into one of the most mind-bending mysteries: quantum gravity. For centuries, scientists have tried to bridge the gap between quantum mechanics and gravity. Newton's gravity tells us how objects attract each other, and Einstein's general relativity shows us how space-time curves. But reconciling these two has been a tough nut to crack. Recently, physicists at the University of Southampton made a groundbreaking discovery. They measured gravity at the microscopic level using levitating magnets and a novel technique. This allowed them to detect a weak gravitational pull on tiny particles. This is a huge leap towards understanding quantum gravity, which could explain black holes, the universe's origin, and even unify fundamental forces. In the quantum realm, things get even weirder. Particles don't behave like they do in our everyday world. Think quantum entanglement, where particles communicate through probabilities. Here, uncertainty rules, and even space-time itself seems to dance to the rhythm of quantum fluctuations. Cosmology, on the other hand, constructs models to describe the universe's grand design. Cosmologists blend theory with observation to explore questions about the universe's origin, structure, dark matter, and dark energy. By decoding the cosmic code, they seek to understand the cosmic canvas stretched across the universe. Now that we've delved into the fascinating world of quantum gravity, let's venture further into the mysterious realms of dark matter and dark energy. Dark matter. Imagine a universe filled with an invisible substance that constitutes most of the mass in galaxies and galaxy clusters. This is dark matter. Unlike the ordinary matter we see and interact with, dark matter doesn't emit, absorb, or reflect light. It remains elusive and invisible to our eyes and instruments. Think of dark matter as cosmic cement. It gravitationally binds galaxies together, preventing them from flying apart due to their rotational speeds. It interacts through gravity, affecting the motion of stars and galaxies, yet it remains undetectable by our telescopes and instruments. The true nature of dark matter is one of the biggest puzzles in astrophysics. What exactly is it made of? Could it be composed of exotic particles? These questions continue to intrigue scientists as they search for answers. Dark energy. Now let's shift our focus to an even more enigmatic force: dark energy. Dark energy is the dominant component of the universe, making up about 69.4% of it. Unlike matter, dark energy doesn't clump into galaxies or stars. Instead, it behaves as a repulsive force, driving the accelerated expansion of the universe. Imagine anti-gravity pushing galaxies apart faster and faster. Dark energy is relatively uniform across space and time, permeating the cosmos and stretching the fabric of space-time itself. The ultimate fate of the universe depends on dark energy. Will it continue to accelerate the expansion indefinitely, or will it lead to a cosmic tear? We're still unraveling this cosmic enigma. What experiments are underway to detect dark matter? Scientists around the world are actively conducting experiments to detect dark matter. Here are some notable efforts. Broadband reflector experiment for axion detection, BRED, developed by the University of Chicago and the US Department of Energy's Fermilab. BRED searches for hypothetical dark matter, particles called axions, and associated dark photons. It takes a broadband approach, scanning across a larger set of possibilities than other experiments, albeit with slightly less precision. Recent results have placed tighter constraints on the characteristics of potential dark matter particles, photons and phonons, at UC Berkeley. Preliminary experiments based on photons and phonons, quantized vibrations, are underway. These multiple strategies complement each other and could help confirm dark matter detection results. Wright Lab experiments. Led by researchers at Yale's Wright Lab, these experiments focus on detecting two popular dark matter candidates: weakly interacting massive particles, WIMPs, and axions. Quantum devices at SLAC National Accelerator Laboratory. Physicists propose using quantum devices naturally tuned to detect thermalized dark matter. This innovative approach aims to explore new avenues for dark matter detection. Now that we've delved into the fascinating world of dark matter and dark energy, let's explore the various strategies scientists use to hunt for dark matter and the intriguing candidates they have identified. How do scientists rule out certain dark matter candidates? Scientists employ a variety of sophisticated methods to rule out or constrain specific dark matter candidates. Let's explore some of these techniques. Direct detection experiments. These experiments aim to detect dark matter particles directly by observing their interactions with ordinary matter. Detectors are placed deep underground to shield from cosmic rays and other background noise. If a dark matter particle collides with a nucleus in the detector, it could produce detectable signals such as scintillation, light, or heat. While no conclusive direct detection has occurred so far, experiments continue to improve in sensitivity. Collider experiments. Particle accelerators like the Large Hadron Collider, LHC, at CERN create conditions similar to the early universe. Scientists search for new particles, including dark matter candidates, by colliding protons at high energies. If a particle consistent with dark matter is produced, it could leave specific signatures in the detector. Indirect detection. Instead of detecting dark matter directly, scientists look for its indirect effects. Examples include observing gamma rays from dark matter annihilation or decay in regions like galactic centers or dwarf galaxies. Observations from telescopes like the Fermi Gamma Ray Space Telescope provide constraints on dark matter properties. Cosmic microwave background, CMB. The CMB radiation carries information about the early universe. By analyzing its temperature fluctuations, scientists infer the total amount of matter, including dark matter and its distribution. Deviations from expected patterns can exclude certain dark matter models. Simulations and constraints. Researchers use computer simulations to model the behavior of different dark matter candidates. These simulations predict how dark matter structures form, affecting galaxy clusters, large-scale structure, and cosmic microwave background. Comparing simulations with observations helps rule out unrealistic candidates. What are WIMPs and why are they popular dark matter candidates? WIMPs, weakly interacting massive particles, are hypothetical particles that may constitute the main component of dark matter. Here's why WIMPs are intriguing. Interaction properties. WIMPs interact only through the weak nuclear force and gravity, lacking electromagnetic interaction with normal matter, making them invisible through standard observations. Mass and speed. WIMPs are expected to be heavy compared to standard particles. Their large mass results in relatively slow movement, classifying them as cold dark matter. Their low velocities prevent them from overcoming mutual gravitational attraction, causing them to clump together. Cosmic significance. If WIMPs exist, they could account for approximately 75% of all mass in the observable universe. The WIMP miracle arises from the fact that supersymmetric extensions of the standard model predict particles with these properties, making WIMPs a prime candidate. What are some alternative dark matter candidates? Let's explore some alternative candidates for dark matter beyond the well-known WIMPs. Axions are low-mass, slow-moving particles that don't carry an electric charge. They interact weakly with other matter, making them challenging to detect directly. Axions are still promising candidates due to their properties and theoretical motivations. MACHOs, massive astrophysical compact halo objects. MACHOs include objects like neutron stars, brown dwarfs, and white dwarfs. These massive but dim objects could contribute to dark matter. Observations of gravitational lensing hint at their presence in galactic halos. Kaluza-Klein particles. In theories with extra dimensions, these particles arise. They have higher dimensional counterparts and could be part of the dark matter puzzle. Gravitinos are hypothetical superpartners of gravitons, the mediators of gravity. If they exist, they might contribute to dark matter.